Problem 2.2-1. The rigid pipe is supported by a pin at B and an A36 steel guy wire between points B and D. If the wire has a diameter of 0.375 inches, determine how much it stretches when the load is applied. Okay, we assume that this pipe is rigid. That means it does not deflect. So when we put a load here of 1,000 pounds, we're going to expect D to move down and C to move down, and when it does, it's going to cause stretching or elongation of this wire, and we can determine how much that elongation is. Okay, I'm going to begin by getting some of the properties of our steel wire. Okay, for A36 steel, looked up in a table, I found that the modulus of elasticity is 29,000 KSI, and the yield strength is 36 KSI. Next thing I'm going to do is find the cross-sectional area of our wire. Okay, the cross-sectional area of our wire is 0.110 inches squared. Now what I'm going to do is find the length of the wire. I know the two sides, 3 feet and 2 feet. I can find the hypotenuse of that right triangle. I take the square root of the sum of the squares of the side lengths, and I get length AC, that's the length of our wire. Now I'm going to draw a free body diagram. I've drawn a free body diagram of the whole structure. I've replaced the pin at B with 2 support reactions. I've replaced the cable AC with a force acting in the direction of the cable. Now, if I sum my moments about B, I can get the magnitude of force in the cable. Summing the forces about B gives me this equation here. I have my force AC, that's the cable force. I'm going to get its vertical component, so I take 3, the side length 3 divided by the hypotenuse, 3.606, and it's at a point 2 feet from B, that's the moment arm, minus 1,000 pounds here at a distance of 6 feet from B, and I can calculate the force in the cable is 3,606 pounds. Now that I have the force in the cable, if I find what the stress in the cable is, I can then use Hooke's law to get the strain. From there I can get elongation, and that gives me the solution. So the next step will be to calculate the stress in our cable. The stress in the cable is the force, 3,606 pounds, divided by the cross-sectional area, which we found above. That gives me 32,780 psi, or 32.78 KSI. Now it's good at this point to do a check. The calculated stress, 32.78 KSI, is less than the yield stress of A36 steel, which is 36 KSI. It's important to check this because Hooke's law, which we're about to use next, only applies to materials that are exhibiting linear elastic behavior. And because our stress is less than the yield stress, we are still in the elastic region. Hooke's law can be written to solve for strain, and we get strain is equal to stress divided by Young's modulus. And that gives us 0.0013. Notice the units cancel out. We can use our normal strain to get the elongation by multiplying normal strain by the original length. In this case, our strain is 0.00113. Our original length is 3.606 feet. Multiply it by 12 to convert to a more convenient unit of inches for elongation, and we get our elongation of our wire is 0.049. That is our answer, and we're done.